Thursday we enter slightly into this open system chapter. So like say mass is this, yeah. So we talk a little bit about the open system chapter. So open system we also call it as control volume because that's what we analyze. And yeah, so in open system, conservation of mass is a theory that is very important for us. But in general, of course, that's just what we assume most of the time lah. Okay, so in both cases, closed system, open system, for us, we just assume the mass are always constant. Okay, so we talk about conservation of mass. So we are talking about mass flow rate in equals to mass flow rate out. So we always assume steady flow, and then we can use this concept for open system. Okay, so yeah, so steady flow. So as I mentioned, we use the assumption steady flow in order for us to be able to assume conservation of mass flow rate. So this is one main assumption that you must have for all open system. Okay, so and then yeah, so this is just how we calculate mass flow rate from volume flow rate, and also how we calculate volumetric flow rate. So volumetric flow rate is just the velocity. So this V here is velocity multiplied by area, and then mass flow rate is simply either density multiplied by volume flow rate or volume flow rate divided by specific volume. So again, these are the things that you basically, it must be to the point that is intuitive to you lah. The moment you see this, you must know how to do all this. Okay, so we looked at, I think we did look at this example where it's just a calculation of mass flow rate, so nothing special here. And then we talk about this special case of incompressible flow. So incompressible flow means that the fluid in play here, or whether it's liquid or gas, or has a constant density. So the density or specific volume doesn't change. So in this kind of case, then you can assume that the volume flow rate in is equal to volume flow rate out because the density is a constant. But always remember that we don't have such thing as conservation of volume. It is always conservation of mass. So in all cases, just assume mass flow rate is constant. Okay, I mean, if you're not very good in differentiating the situation, then you just cancel off accordingly. But so again, so mass flow rate is always a constant, not volume flow rate, because the density can change. So you can see in this example as well. So it's just a simple illustration, but you can see that mass flow rate at in and out, they are both 2 kg per second, but the volume flow rate can change. So the variable that can change here, usually it would be either velocity or area. No, sorry, not velocity, area. Velocity, area, or density. So these are the things that might change. Okay, then we do have one example here. So a garden hose attached with a nozzle is used to fill a 10-gallon bucket. So the inner diameter of the hose is 2 cm, and it reduces to 0.8 cm at the nozzle exit. So the normal hose that you use at home is an example of a nozzle as well, if you have the attachment at the exit. So if it takes 50 seconds to fill the bucket with water, determine the volume and mass flow rate of water through the hose and the average velocity of water at the nozzle exit. So try this out based on what you have just learned. So this will be about the conservation of mass, so mass flow rate. Just a quick one. It shouldn't take too much time. you can use this conversion for gallon, and in this case, when you're dealing with liquid water, we can more or less assume that the density is constant. Okay, I think I'll just show the answer for this one. Okay, so again, let's just look at the question. So you are told that inner diameter is 2 cm and exit would be 0.8 cm. So that's what you have lah. So if you have a nozzle, then this will be the 2 cm part, and this will be the 0.8 cm diameter. And you have the total time to fill the bucket. Essentially, that's all you have. But of course, again, like I said, if we are dealing with liquid water, we can mostly assume that this is an incompressible flow, because if you just look at the thermodynamic properties table as well. So for water, if you look at the saturated liquid side, you can see that the specific volume doesn't really change much. They're all quite consistent value. So when you're dealing with liquid, mostly you can just assume that they are incompressible. So we're talking about pure liquid here. So once it gets past the saturated state, then that's different story. Okay, so here we can make this assumption. So as I mentioned, we can assume that water is incompressible. And then again, for open system, you should always assume steady flow. And the last one, don't care lah. Meaning I won't expect you to write this for the exam, let's say if this comes out. So, but the first two will be the important assumption for this case. So once you know that it is incompressible, then we know that density or specific volume doesn't change. So volume flow rate in and volume flow rate out is the same. Then you can find out the volume flow rate, because in total you have 10 gallons of water and they flow through in 50 seconds. So from here you can calculate the volume flow rate. So of course, if you want to convert this to meter cube, that's fine as well. In this case, we don't really convert because it doesn't really matter. Question doesn't really ask. So in general, if the question doesn't ask for any specific unit, you can leave them in any form lah, as long as the answer is correct, of course. So then we know that every liter of water will be 1 kg. So from here, you can also find out the mass flow rate, which is actually the same value. Okay, so B asks for the, what does B ask for? The average velocity of water at the nozzle exit. So here we focus at the exit. So again, we know that the exit has the, what's this? Exit has the same flow rate, right? Because density doesn't change. So all you need to do is to calculate the exit area. So once you calculate the exit area, so in this case, then you have to change the units, because this will be in terms of meter square. So you have to change the liter to meter cube, and you will be able to get the velocity at the exit just based on this. So just simple calculation here. Okay, so shouldn't be too tough here. Or anyone needs me to stay in this at this slide for a while more, or I'll just progress. Okay, 3, 2, 1, then let's move on. Okay, so now, once we pass that, here we will have to look at proper energy analysis for open system now. So in closed system, when we were dealing with closed system, you should be able to notice that the energy that we deal with is mainly the internal energy, right? So that's why we have our default equation, Q minus W equals to delta U. So whatever that happens cause changes in the internal energy of the system. That was what we learned in closed system. But in open system, that is no longer the case. So the main reason here is that open system, we now have what we call the flow energy, because we have a constant flow of fluid. So this is in a way, this is a component of the mass flow. I mean, it's not exactly that, but this is the energy that is moving. So flow energy is basically the work required to push the mass into or out of the control volume. This work is necessary for maintaining a continuous flow through a control volume. So basically, it's the work in order to carry the fluid, in order to move it, basically. That's what flow energy is. Okay, so here we try to define this flow energy in terms of the normal work that you study, meaning force over distance. Alright, so what you can imagine is this. So remember that we said that for open system, we need to define a space that we are studying that we call control volume. So you imagine this is the control volume. And you imagine that you are just carrying one specific amount of the fluid. So the flow energy will be the energy that you need to push this amount through or into the control volume, and then later on out of the control volume. So in that sense, So this will be the mass flow crossing the system boundary, and this is the system boundary. Alright, so in other words, you can also imagine that this as a closed system. So you have a piston here, you also have a piston here. So you push this piston, and then this piston will push the fluid through the control volume, and then when it goes out of the control volume, this piston will get pushed away, push off. Basically, this you can imagine it this way. So from here, the flow work or flow energy is simply, so the force multiplied by the distance. So this is the force, this is the distance that it moves, and force is pressure multiplied by area. So we get the equation PV, pressure and volume. So actually, if you imagine this as a closed system, right? Let's say if your boundary is around this whole thing, can you see that this is similar to one thing that you learned in closed system? It actually is kind of like boundary work. But now it's open system lah, so it's no longer boundary work, because in this case our boundary is actually fixed. But this is actually similar to boundary work. So like in boundary work also, we did define that the boundary work is PV, right? It's just that it is in a slightly different sense now. So in this case here, the pressure itself is actually the one that changed because the flow is moving. Okay, so this is the flow energy. So meaning, now when we look at the energy equation, so we used to say U plus KE plus PE, right? So total energy of a non-flowing, so this case is a non-flowing fluid, meaning our closed system. This was the energy change of the system, right? So just a revision. We have internal energy, kinetic energy, and potential energy. So this was for closed system. For flowing fluid, meaning for open system, now we are adding one more term here, which is PV. So the energy by the pressure, because without the pressure, of course, there's no flowing fluid. Okay, so in this case, we are adding one term here. So this one term, remember we did one thing with the closed system, whereby if we have constant pressure process, of course here is slightly different in meaning, but in closed system we say that when we have a constant pressure process, we can combine these two terms using this, right? So for open system, we combine it directly. So in essence, U plus PV become H. So this is the energy change of the system for open system. So the flow energy is automatically taken care of by enthalpy. So we don't care about the PV anymore, because now we have the enthalpy to take this into consideration. So in fact, this is the main reason for defining the property enthalpy. So for flowing fluid, technically speaking, the total energy consists of 4 parts, but then we simplify the PV term and also the U term into enthalpy. So this is the new equation for open system. Okay, so let's just have a quick look, okay, at, let's say we have a system where everything changes. So in this case, this can be a bit confusing, but because sometimes we have a bit limited alphabet. So this C here is actually velocity. This C is also velocity. Okay, sometimes we do use C as velocity. So here you can see that, so let's say in this case, we have change in height. We also have change in velocity. Okay, so for open system, we assume, so mass balance, again, we assume that we have steady flow, so mass flow rate is a constant, so we only have one mass flow rate. Okay, then, so for the energy balance, for open system, in general, the way that we assume is that we assume that this is 0. Okay, we assume that the change in the energy of the system is 0, because what comes in equals to what goes out. So then we move E in equals to E out. So E in will be Q in, work in, and then the energy term just now. So enthalpy, kinetic energy, potential energy, gravitational potential energy, then equals to out. V2, then same thing. Okay, so remember in tutorial I mentioned that sometimes it's just a matter of perspective. Actually what we are doing is exactly the same. So actually this is still the case in this situation. So let's say if you move everything, if you move all the Q to the left, you move all the work to the right, you see what ultimately what you get is actually this. Equals to delta H, then plus the KE term plus the PE term. Sorry, no tablet, so this is how I can write. Okay, so can you see that? So technically, if you just rearrange, you are still getting the same equation for the closed system. But for open system, instead of delta U, it is just a purely delta H case. So one way to remember this, basically these two has the same equation. If you are open system, you are dealing with change in internal energy. If you have open system, then you are dealing with enthalpy. That's the basic idea of this. Okay, so for open system, but usually if we are just talking about like theory sense, we usually put it in this way rather than this. So when we have this way, then so essentially what you do every time we see open system, you write this whole equation out, then you cancel off one by one, depending on what is available to you and what is not. Okay, so so here this is just something that we just to show you the steady flow assumption. So under steady flow condition, the fluid properties. So under steady flow condition, the mass and energy content of a control volume remain constant, and the fluid properties at an inlet or exit remain constant. So if you have steady flow, mass flow doesn't change, the condition or properties or the states of the inlet will remain constant, outlet will also remain constant. So meaning they won't change over time, then we can safely found their respective properties through our analysis. So again, this is an important assumption for all open system. Okay, so here's an example. Now that we look at an open system, I'll just discuss this. So air flows steadily in a pipe at 300 kilopascal and 77 degrees Celsius and 25 meters per second at a rate of 18 kilogram per minute. So you are given the pressure, temperature, and this is air. So again, go back to closed system when we talk about the steps of analyzing this kind of question. So first thing, you need to identify this and open or closed system. So we know, obviously we are not an open system chapter, so this is an open system. By exam, you need to identify So second, you need to identify what is the substance that you're dealing with. So here we are dealing with air. So air flows steadily in a pipe. You are given these properties. So next you look at what properties are given to you. You have the velocity and the mass flow rate as well. Determine the diameter of the pipe, the rate of flow energy, the rate of energy transfer by mass, and also the error involved in part C if the kinetic energy is neglected. Okay, so this question is actually for what we use to prove a certain thing, which I will tell you later. Actually C part C basically. Sorry, part D. Okay, so how do we determine the diameter of the pipe from the information given here? The equation should be pretty straightforward here. Think about it, how do we get the diameter? Or rather, instead of telling me how to find the diameter, what are the properties here that can be related to diameter? You only have 4 information here, right? The main one that can be related to diameter will be no, wait, based on here. You can just say all of them, right? The one that's directly related to diameter would be this one, right? Because you have mass flow rate and velocity here. So what's the equation for mass flow rate? Okay, so if you look at this, you have mass flow rate, right? What is the equation for mass flow rate? It will be rho AB. So V term, you have the answer. You need to find A for you to find density. Diameter. So meaning what you need to find here is density. So how can you find density of air? Yes. There's no table for you to find density of air. Water, yes, not air. Or if you write it in specific volume term, then it will be A V over the small v. So whichever one, you need a density or specific volume. But what equation will give you this value? So actually, in general, this is actually how you can solve most questions as well. Try to look for what you need, like through all the linkage. So like I said, this is my set of answers. So if you look at answer, usually this is not how they go, because the answer know what they want. They will just find what they want right from the start. So this is how this is just me showing you how you can identify what you need to find. So based on this equation, you know that you need density or specific volume. So always bear in mind one thing. I actually mentioned it in the previous classes as well. When you're dealing with air, we are assuming that it is ideal gas, right? And if it is ideal gas, what can you use? Ideal gas equation. Okay, so for ideal gas equation, so these properties you can get from table. This is at 350 Kelvin. So for ideal gas, right, you can use the ideal gas equation. So PV equals to mRT. If you move this m over, so the equation becomes the specific volume equation. So this is a small v. And you move P over, so you can use this equation to calculate the specific volume of the air. So then now you get the specific volume of the air. You can calculate the area and subsequently the diameter of the pipe. Okay, so again, if you see air, you see temperature, pressure given, there's a high chance that you can make use of ideal gas equation. Just don't use this for water, that's all. This for air only. I mean ideal gas lah, not to say air only, but it's for ideal gas. Is everyone clear about part A? So technically speaking, right, you can also use it in another way round, meaning you can actually sub in the mass flow rate term here, and then the volume flow rate. Then you will get a volume flow rate. Then you can use the volume flow rate and the velocity to get the area. Basically, it's still the same thing. Okay. Alright, so then now we look at part B. So B, once you solve A, then B should be more straightforward. Because B, you are just looking for rate of flow energy. So for B, you can directly apply the equation, which is, so for flow energy, remember we said it was PV, but that was the capital V lah. So now we only have the small v, you multiply by the mass flow rate, and you should be able to get the answer. So the answer asks for rate of flow energy, so obviously it is going to be in terms of kilowatt. So again, always remember this, when we are calculating for all this energy term, right, unless it is specified that you're looking for specific energy or energy per unit mass, we always want it in terms of either watts or joule. We don't want the answer to be in terms of per kg. Okay, so for B, we are only looking for rate of flow energy. So in C, we want the rate of energy transfer by mass, meaning we want the entire energy transfer, not just the flow energy. So the entire energy transfer in this case is simply H plus KE. Okay, so you apply back the open system equation just now, or in this case, of course, we don't have Q, we don't have W. We also do not have gravitational potential energy. So what you are left with is just H and KE. So in this case, the H is simply CPT, because again, we are talking about air here. So CPT is for enthalpy, CVT is for internal energy. So you can use CPT plus the KE term, but again, don't forget about the units. So what do I mean by the unit? When you use CPT here, the value that you get, you will usually in terms of kilojoule. But when you use V squared over 2, this is usually in terms of joule. So that's why we need to divide by 1000. Okay, so D asks us to calculate again this value if we are assuming that there's no kinetic energy. So this one actually is the same calculation, but you just take out the kinetic energy term. So you will notice that once you take out the kinetic energy term, right, you can see that this value is not very significant. Right, with kinetic energy is 105.94, without kinetic energy is actually 105.84. So you will often see in like our application here in open system. So even though like it makes sense that in open system there is a flow, there will be some velocity change, so KE definitely will change. But you will see that a lot of the time we will just ignore this term because the value is not significant at all. Okay, of course, if the question tells you that there is a change in velocity, this is a velocity, this is a velocity, then you take into consideration that. But most of the time, you will see that we actually ignore them. Okay, so food for thought here. So let's say we come back to this water dispenser or drink dispenser. Let's say you open this up and to refill water. and you never close it. Okay, just open it. Is this a steady flow system? Why?
No.
No, then why?
Because there's nothing to unless you say the movement of it filling up lah. But if you just open it up, there's no steady flow.
Your explanation is correct, but I prefer a bit more.
Atas a bit, I don't know.
Yeah, not really atas a bit, but yeah, use back the term that you use here basically. Yeah, so the answer is no, because if you turn this on, the water inside actually will, amount of the drinks inside will actually reduce. So meaning mass is actually not conserved. So of course, so again, same as what your friend explained here. If you have another inlet that's keep refilling it while you are taking the drinks, then yes, this can be considered a steady flow system. Otherwise, this is not. Alright, so for open system, okay, never mind. I think we'll take a 5 minutes break first. After the break, we will look at 1, 2, 3, 4, 5, 6, 7 types of different steady flow devices and how we can analyze them. Technically speaking, the main one is just 5 or 6 lah. The main one is the 6. The last one is actually just a random example in a sense. Okay, so after the break, so you come back at like 8:55 or 9, then we will look at all these different examples or cases. So for those of you who came in late, this is the code.